The purpose of this pencast or screencast is the principle of conservation of momentum and what is called the impulse change in momentum theorem. The context for both of these things is collisions, so we're going to focus on collisions. First of all, it's pretty common for us to draw these or start off with a before and after picture. So before, I have object A traveling this way, and object B, let's say it's at rest. Let's also say mass A is larger than mass B. What do you think the after picture is going to look like? Which way does B go? Which way would A go? And you may have guessed B is going to travel this way now. You may have guessed A bounces backwards. You may also have guessed that A moves forward still. And I'm not going to tell you yet. Maybe A continues, maybe it doesn't. But it's pretty certain that B would move to the right because it got hit and got pushed to the right. We have another type of collision that we could talk about. There's this one here where the two objects, let's again go with A moving to the right and B at rest. Now A and B stick together, and which way would they go? It seems like it makes sense that they'd go to the right. You might also think that they'd move to the right slower than A was moving in the first place, which would be correct. And still, there's more. We could talk about this type of event, where the two items start together. Let's suppose they're both at rest. And the explosion takes place. Now what if MA is still greater than MB? Well, you'd think that B is going to go to the right and A is going to go to the left, but I wonder which one's going to go faster as a result of the explosion taking place. The principle of conservation of momentum, or depending on how you look at the problem, the impulse change momentum theorem will be the guiding factor to figure out how the after picture looks depending on these certain characteristics of the before picture. We'll go ahead and set that up. So let's go ahead and look. First of all, the premise of this is stuff hits other stuff. So we have collisions taking place. We could connect to Newton's second law, that says, or Newton's first law, or try again, Newton's third. The force A exerts on B is the same size as the force B exerts on A, but directed oppositely. So that's Newton's third law. That's true of all situations, no matter what. Whenever two things interact, they do so with equal size force directed oppositely. If this force of contact is the only force causing acceleration, we can then connect to Newton's second law. That's B. If net force equals ma, then we can do this. The reason that this is the mass B and that's acceleration B is because this is the force A exerts on B. So B is the object. Over here, A is the object, so we're interested in the mass of A and the acceleration of A. Okay, so this statement here, it says the same thing as Newton's third law. I could write it another way still, just doing another substitution. Because acceleration is defined as the change in velocity over time, I can do that substitution as well. And that says the mass of B times the change in velocity B over time equals the opposite of the mass of A times the change in velocity of A over time. All three of these statements right now say exactly the same thing, and that's the forces are equal in magnitude, opposite direction. But now I can do a little manipulation. This time is the same as that time. So it effectually cancels out. So I could look at the mass of B, change in velocity B, equals the opposite of the mass of A, change in velocity A. Now this is actually something different than all the previous things. All the previous things just said forces between the two are the same size, opposite directions. This is actually a little different. This is now just talking about the product of the mass of an object and its change in velocity compared to the mass of the other object and the other object's change in velocity. Here's what the momentum is. I'm going to define momentum mathematically for you. Momentum, symbol is P, it's a vector quantity, is the product between mass and velocity. So restating this down here, that says the change in momentum of B, it's a change because this had a delta, is opposite the change in momentum of A. So each object changes momentum, and the amount of change of momentum is related to both the mass of the object and the change in velocity of that object. Okay, there's more to do. So let's take a look at another. Let's go with that and continue, I guess. Mass B, change in velocity B, equals the opposite, mass A, change in velocity A. Now remember, deltas are finals minus initials, so I can rewrite that as V final minus V initial. Those are both for B. And this is the opposite of mass A, V final A minus V initial A. Now it looks worse, but it's going to get better, or at least more useful. If I distribute the mass I get something like this. Or not that. V initial A. Okay, maybe it doesn't look super clear yet, but I could rewrite this as mass A VA initial plus mass B VB initial equals mass A VA final plus mass B VB final. You might take a little bit of time to confirm, to make sure, to prove to yourself that I didn't cheat somewhere, that this result up here with some algebra will get you down there. That's kind of important. That bottom statement ultimately says the total momentum before equals the total momentum after. And that right there is a statement of the conservation of momentum. So if two objects hit each other, and they're the only two things involved, there's no other external forces, then the momentum in that collision is conserved. What's interesting, or at least I think it's interesting, it works for this. Here we go. Mass A V A initial plus mass B VB initial equals mass A VA final plus mass B VB final. And beyond just working, it actually looks, to me at least, it looks like the picture, right? There's an object, there's an object. The two objects started apart and they each had a momentum term. Afterwards, they collide and they're separate again. They again have their own momentum term. So this is a start apart, end apart collision. It's also called an inelastic collision. And the conservation of momentum works. What about this one? Well, let's see. Here I have an MAVA initial and an MBVB initial. They each have their own momentum. And what's happening over here? Well, there's still an MAVA final and an MBVB final, but they're behaving as if they are one mass, MA plus MB, V final. And if you wanted to distribute that V, then you'd see the individual momentum terms. But I typically don't distribute that V. Instead, I think it's interesting that the picture, right, one object, separated by a plus sign, these two behaving as one single object, and there's my total mass. So I have two separate momenta, and then one total one. This is called a completely inelastic collision. Ooh, learn to spell. I'll try that again another day. Completely inelastic collision. And again, the conservation of momentum works. This also works. But here, I have MA and MB together in the beginning with their combined initial velocity, which could be 0. And that's going to equal MA VA final plus MB VB final. So they started together as one mass, they ended separately. That's kind of cool. Again, principles of conservation of momentum. That one is called an explosion. So there we go. That's when momentum is conserved. When we treat the system as closed, where the two objects are acting on each other and there's nothing else going on, then we have momentum conserved. But wait, there's more. If we're looking just at block A, that's our object, and it happens to hit block B, but we're treating B as an external thing. So here's A, and there's an FG down, an FN up, and when it collides with B, B acts on A, right? And that's the only force. So the force B exerts on A equals the mass of A times the acceleration of A. And we've already written that also as mass change in velocity over change in time. And when I multiply the time across, I get this. The force B acts on A multiplied by time equals the mass of A times the change in velocity of A. You might, maybe, perhaps recognize this here is a change in momentum. It's the change in momentum of A as a result of an external force acting on it. The product of force and time is called impulse. Also a vector quantity. Impulse, for some reason, is a J. I'd like to say impulse because it sounds more fun. But it's impulse. Impulse equals the change in momentum. So this one, if we have an external force exerted on an object for some amount of time, that force delivers an impulse to the object, which changes the object's momentum. This is very similar to the work change in energy theorem, where if we have an external force performing work on a particle, then that external force acts for some distance to change the energy. So very similar, except different. This is force times time as opposed to force times displacement. All right, so that's it. That's in a nutshell what you need to know to get started solving problems, thinking about problems, and thinking about collisions from a standpoint of the principle of conservation of momentum or the impulse change momentum theorem.